introduction and for the, hang on, let me get rid of the pop-up. Okay, thank you. Okay, thanks for the introduction and for the invitation to speak. And so what I'm going to talk about is some of the work we've been doing at I24 and at SAC and at different XFELs and at different XFELs work around the world. So yeah, so I'm based. Well, let me change. Here we go. Okay, so I'm based at Beamline I24 at Diamond. That's the beamline I'm responsible for. And I24 is a Microfocus MX beamline. So traditionally, and the original aim of the beamline was to kind of tackle conventional cryo pin-based Microfocus MX, but in recent years we've kind of expanded the reach to also include serial crystallography. And so we've got quite a small team at the moment. There's 5 of us, and basically we work together to try and kind of develop new methods and deliver new tools to users. So we're a tunable beamline, 8 to 25 kV. Really, as you'll see in a minute, we're kind of pushing towards the higher end of that energy range. We've got relatively high flux density and an adaptable beam size as well. That's kind of quickly changeable between different focuses. And what we have, and that I'll kind of try and introduce a little bit over the next couple of slides, is we have kind of this modular sample environment that makes things nice and easy to swap around. It lets us change between different experiments, and we've got some different detectors available as well. So the Eiger and the Jungfrau, which I'll mention towards the end of the presentation. So really kind of the premise and the ethos of the beamline is that we're kind of trying to help users collect good cryo and good serial data from difficult crystals, and then also consistently trying to introduce new ways of collecting data, novel ways of collecting data that can help the users. And I'll introduce a couple of those as we go through. So I kind of mentioned that we kind of have this kind of modular approach and this flexible approach, and that's kind of illustrated by the goniometer that we have. So we have a vertical goniometer to point up, the pins point upwards, and it's kind of got this kind of interchangeable hat, if you like. So this hat can be kind of lifted on and off pretty quickly. So, within kind of a few tens of seconds, and that allows us to change between different types of experiments. So it gives us a lot of flexibility. So we've got your traditional XY pin. We can move to fast Y, which we've been commissioning for looking at doing faster rastering over samples, fixed targets. You can also use it to accommodate the extruder, or if we've got something kind of completely new, we can just swap to a breadboard and build something completely new on the goniometer on the fly, and that's something that's been quite useful. And and that's kind of been a real asset to the beamline, I would say. So what I'm going to focus on really for all of the talk today is the fixed target approach. So this is kind of really our workhorse for serial experiments. And I think what we find, what's attractive to us, is it's kind of a time and sample efficient way of realizing serial crystallography, both at Diamond and then also at other sources as well. So what we've done is they've got the setup at Diamond there shown on the left, but we've also taken the same hardware to Sackler, PAL, other sources beyond those as well. And you can see it's essentially the same hardware put together in different ways. So kind of, if you like to kind of stretch the Lego analogy from the image I showed earlier, it's kind of using these building blocks to kind of put the experiment, to facilitate the experiment at different sources. And this is something that's worked quite well for us, and then also our users. So it's good for our users because they can use the same types of sample preparation, and they're familiar with the setup, even if it's a different source. So our workhorse for serial crystallography is these silicon chips. They're about 30 by 30 mil. They come with a range of aperture sizes, and we get 25,000 apertures per chip. So these chips were originally developed between Diamond, Hamburg, and Toronto, and then this is the version that we've ended up with at Diamond, and that we're using regularly on the beamline. So if we look a little bit closer, what the chips look like, the chips are kind of this 2D array, but when you look a little bit closer, they're not flat. They've kind of got these funnels which when the liquid is pipetted over the top, the crystals get pulled into the funnels. And so when we go through, we're going to shoot at each of these apertures in turn. And you can see on the microscope image here, we've got the crystals. They've been pulled down into the apertures of the chip, and then we're going to shoot through the mid center of each aperture. And we'll come to later, what we'll come to later as well, an advantage of this is that these are kind of almost independent experiments. So we can fire a laser into each of these apertures, and the adjacent crystals are then shielded from the laser so that you don't get cross-contamination between the apertures. So once the crystals are loaded onto the chip itself gets put onto a holder, which is then sealed, and then that's then ready to go onto the beamline. Chip goes onto the beamline and gets rastered through the X-ray beam. So here we're kind of moving to a position, stopping, collecting the image, moving to the next position, and so on. And we can do that if we're doing this type of experiment at I-24, then we can go through all 25,000 apertures in around about 10 minutes. So it's quite quick throughput. So moving on to the types of experiment that we can do. So I kind of mentioned the Jungfrau detector briefly earlier, but I'll come back to that and just look at the Eiger the Eiger detector in the first instance. And what's special about the Eiger that we have is the material that the sensor is made from. So it's this cadmium telluride sensor. And the special thing about the cadmium telluride is that the cross section doesn't fall off as the X-ray energy increases. So that has a big advantage for MX because as the X-ray energy increases, the diffracted intensity that you can record per unit absorbed dose increases significantly if the detector if a suitable detector is used. And I think it's pretty well known now that dose drives change in crystals, and that's not always a wanted change. So if we can minimize the dose or maximize the data collected per unit dose, then that's highly beneficial. So by using the Eiger detector, we can shift our default operating energy to these higher energies and get more data from each crystal. So at the moment, and this will change in the future, but at the moment, our default operating energy is about 20 kV. So kind of in the middle of the range shown here, that is something that will increase, move or shift to higher energies in the future. But now we feel that's a good compromise of kind of the benefits of high energy data collection versus the available flux. So recently, the plot shown here was work done by Selena, or led by Selena quite a while ago, but more recently, what one of the guys working on the beamline, Do Hom, what he wanted to look at how do these gains and can we quantify these gains as a function of energy for serial crystallography, and do the gains do they carry on for serial experiments? So in order to achieve that, what we did is we collected fixed target serial data at multiple energies ranging from 12 to 25 keV. One of the key aspects here is these were super low dose experiments. So this is just less than half a kilogray per image. So this is a really low dose, right? So this is, I guess, 5 orders of magnitude less than what you would think of as being a dose limit for cryo MX. Another so 3 orders of magnitude less than room temperature dose limits. These are really low dose experiments. We use the same dose or all energies that we collected the data for. So what we can see here, what we can see in the first plot here is as you would expect from the theory, is for the same dose you get increasing intensity as a function of energy. So as the energy increases for the same dose, you get increased diffractive intensity. Take a further look at how that affects I over sigma I. You can see there's two effects in play. So the first is that as the number of crystals in a serial data set increases, that I over sigma I improves. That's kind of what you expect. But then that's accompanied by the complementary benefit of that you get when the energy is increased. So you have higher energies, you get a significantly improved I over sigma I. And so this is for the data set as a whole. But if you look at the per reflection statistics as well, we've got histograms for looking at the data set for all the reflections in the 12,000 in the data set consisting of data set formed from 12,000 images. You can see that I over sigma I, the histogram, the mean value slowly shifts to increasing I over sigma I, and the shape of the distribution stays broadly the same. So this is kind of backing up that this is a real gain that we see as a function of energy. So what does that mean in terms of the scaling statistics? So if we look at the data set made up from 12,000 crystals, you can see this is what Dohan's highlighted here in the kind of slightly yellow regions is at the higher energies, what you see is consistently you're kind of pushing out to improve the data, improving the data as the energy increases. So the CC half is increasing, the R split is decreasing, and you can kind of intuitively see that what the result of this is, it's kind of increasing the resolution of the data that you obtain, and that's what's shown here, right? So there's some variability. It doesn't scale exactly with energy from just I think just some inherent variability within the experiment. But the general trend is that as the energy increases, the resolution of the data you can obtain improves. And then that's kind of, again, twofold. So as the number of crystals in the data forming the data set increases, but then as the energy increases as well. So you can see if you have a finite number of crystals, then you can get better data, higher resolution data if you collect the data using higher X-ray energies. So, and that's something that I'll come on to in a minute, that even for serial data sets, especially the synchrotron, it's important to think about minimizing the dose. And that brings us on to X-ray induced changes in serial crystallography. And then there's two aspects of that I wanted to talk about today. So that's X-ray induced changes at the synchrotron, but then also at the X-ray free electron, a laser as well. So for the first set of experiments I'll talk about data collected at Diamond, and then also data collected at Sackler. So something that the fixed target approach is quite amenable to is tracking X-ray induced changes. And it's good because we're kind of moving the crystals through the beam in a controlled and reproducible way. So what that enables us to do is it enables us to collect multiple images from each crystal. So what we can do is we can go to position 1, collect 10 images, go to position 2, collect 10 images, and so on. And then what we can do is selectively bin the data to get a series of dose resolved structures. So this is work that Ali did again a few years ago, but on what we can see here is looking at we looked at a heme containing enzyme, which is a DTPAA, And really a telltale sign of damage in DTPA is the elongation of this bond here between the iron and the water. So if we look at the lowest dose data set, so that corresponds to about 33 kilogray in this case, bonds just under 2.5 angstrom. As we cycle through, we can see as the bond length starts to increase. And then we can see here then that if we plot the bond length as a function of dose, then the bond length increases. And this is probably reflects a changing changing populations within the crystal between different subsets of sorry, I can't think of the word. Uh, 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 but reflects the the occupancy of different states with water closer or further away to the further away to the iron. But what we can do here, what's quite interesting, is you can see, well, what if the dose was 0? What if we did a 0 dose experiment? You see here then the bond length becomes just under 2.4 angstroms, and we can complement that with the structure that we obtained with data collected at Sackler, and you can see that agrees pretty well with the bond length obtained here. So kind of as an intermediate conclusion, I think, or what is an intermediate conclusion is really that at the synchrotron, even for serial experiments when the dose is relatively low, we're kind of seeing these irreversible changes, and that's a problem for SSX, and it starts to place a premium on XFEL metalloprotein structures. So what then that I think then one of the things that then leads us to ask is, or is this structure we obtain at the XFEL, is this damage free? And so that kind of leads on to the next question that I wanted to ask, which is exactly that. So are the structures that we're obtaining at the XFEL, are they damage free? So certainly when we first started collecting at the XFEL, we didn't put a lot of thought into the attenuator choice in terms of what is happening inside the crystal within the duration of the pulse. So the main criteria we're thinking about for attenuator choices is the detector being saturated. So what we wanted to try and think about and look into is the electron density that we're observing, is it really pristine, or are we seeing changes? So does diffraction before destruction, is that equal to diffraction before damage? So at an XFEL, when the beam interacts with the sample, what's happening? So essentially the same as at the synchrotron. So we get this photoelectron absorption. That's the dominant process. Get most of the absorption of atoms with of higher Z, and then there's two ways in which the atom can relax, right? So majority will relax via the Auger decay. And so the majority of atoms are going to start losing 2 electrons initially. And this is what starts to drive the Coulomb explosion in the crystal. And then the worry is then for long or very intense pulses, then this process starts to occur multiple times within the duration of the pulse. So what might we expect to see? So we start thinking, might expect to see oxidation rather than reduction, changes at heavy atom sites, and more dramatic changes if we have higher beam intensities and longer pulse durations. And that's kind of really been highlighted in the literature to date. I think the one outstanding experiment really is by Carol Nass and Ilmer and co-workers, and then most of the rest of the work in the literature is through simulations which kind of back up these premises. So To probe impulse damage in SFX, what we wanted to do was collect a series of SFX structures while we systematically varied the pulse duration and then also the intensity. So we were able to do that. XFEL, which is, if you've ever been or if you've not been, is kind of hidden here in the woods, just across the river from the Swiss light source. And at XFEL, we had very lucky to have very good collaborators. With a lot of hard work from Didier and Philippe, what they were able to do is kind of two key things, really. So they were able to achieve a consistent variation in the pulse duration of the XFEL by varying the electron beam and by varying the electron beam parameters. But crucially, what they were also able to do was directly measure these pulse durations. So this wasn't a case of, yeah, we think it's about 8 femtoseconds, or we think it's about 50. They were able to change the parameters and then measure and then directly measure the pulse gyrations. So we could really see what we were using to collect the data. In terms of data collection, this kind of looks somehow familiar. It's kind of a closely related descendant of the fixed target setup that we've been using at Diamond. So you can see it's quite a similar holder. In this case, sits on top of almost like a traditional pin type holder, but it's the same idea, and it's not a silicon chip in this case. It's a kind of a mesh, but again, it rasters through the X-ray beam, and so we could collect data by varying the pulse duration and varying the pulse energy as well. So we, for these experiments, used two different enzymes. So we used the D2PA that I introduced earlier, and then thalmatin, which is a relatively well-known standard, but in this case, interesting because it's very disulfide heavy, right? So we've got these 8 different disulfide bonds to look at. In terms of data quality, in general, good. And I think the main takeaway from this, it wasn't at all a function of pulse duration or intensity. Data quality variation was really just lower quality was data sets with less hits. So if there was less hits, we got slightly inferior data. And resolution cutoff, fairly consistent, slightly better resolution for the higher, more intense, higher intensity data, but really it's kind of limited by the area of the detector that we were able to use. So on to the key question, which is, do the structures obtain change? So intuitively, you would expect the shortest pulse duration, lowest energy to be the least affected by X-ray induced changes. And this is the structure that we obtained. If we increase the pulse energy and duration, see things look pretty similar, and then increase again, and then again, no dramatic change. And that's kind of highlighted here a little bit more clearly. We can see the bond length is essentially identical across all the experiments. Certainly doesn't change outside of the error associated with the measurements. So that's the initial conclusion. If we're using the typical beam parameters, then the models that we obtain look identical, and we also saw no changes in the thalmatin. So if we make the assumption that the shortest pulse duration, lowest intensity dataset provides a damage-free structure, then I think our interpretation is then that all of them do. But to move on, what we wanted to do is then try and more actively look for changes. So if we assume that damage is occurring somewhere in the samples, what if we actively look for this and see what we can see? And just to highlight here that I kind of mentioned the dose several times. And for these experiments, we're using this average dose in the exposed region as calculated by rad dose XFEL. So that factors in two things. So it factors in two things with respect to the beam. So it's the beam intensity, but then also crucially the pulse duration as well. So it's if you have the same intensity at two different pulse durations, you'll get two different ADER doses. Okay, so if we look at the riddle maps and try and make difference maps between pairs of data sets, this should offer a more sensitive probe, and we can look at predicted damage sites. Okay, so and you can see here we can start to see hints of differences and between the data sets. But what we wanted to then try and think about was is there kind of any systematic variation? So we can kind of do what we can do is we can do a pairwise comparison, where if we compare a low dose data set with a high dose data set, and if the differences are a function of dose, what we should see is the biggest changes here. And then as we push out up towards the diagonal, then the changes should systematically become less. But what we see is that, there's kind of no kind of systematic trend. Everything looks fairly consistent throughout, and that's kind of backed up by this plot here. You can see there's not an obvious trend. It just kind of looks like a flattish scatter plot. And again, if we look at the how the length of the bond varies, then that looks fairly flat as well. And let's say exactly the same if we look again at the tryptophan. You can see there's some data set. There's one data set that seems to vary a little bit more than all the rest, but otherwise there's no systematic trend. There's no kind of clear increase or decrease as a function of the difference of dose. What about, does anything happen anywhere else? So we looked at in the beta sheets. This is something that Carol and that saw in their data. You can see these changes in the beta sheet, where you can consistently see differences and, if you like, damage in the same places. But what we found is that it seems to be quite subtle, and again, there's kind of no clear systematic trend. Okay, so just to conclude on the damage front, I think what we see is that the structures we obtained with different pulse durations and intensities are really extremely similar, and so we might be getting site-specific damage, but it's not significant enough to affect the coordinates that we obtain. And that premise seems to be true over the entire pulse duration and pulse intensity range that we could access at XFEL, which is pretty typical for XFEL experiments. So 8 to 50 femtoseconds, 10 to 100 microjoules. Whether this premise is true as the intensity of the pulses increase, that is unclear, and that's something that we're going to follow up on in the future. So for the last couple of slides, what I'd like to do is just then go back to I-24 and describe some of the experiments that we're continuing to do at Diamond. Okay, so yeah, so I kind of mentioned at the start, we kind of got this kind of modular approach that we can use. And I've described some of the static and dose-resolved experiments, but we can also do substrate-driven experiments and light-driven experiments. And something else that we think is quite important is not just, if you like, the flexibility in the beamline hardware, but then also the ability to kind of make changes and introduce things that users kind of find useful or users have requested. And a lot of the things that I'll kind of point out we've kind of been pushed to or requested from different user groups. So something that has been quite popular is the ability to make the fixed target experiments kind of completely anaerobic. So what we found is if we use this certain type of film, this eval film from Kurari, then this is oxygen impermeable, so oxygen impermeable, so we can start to look at anaerobic structures. And the eval's good because it also has other properties that kind of work particularly well for the experiments that we want to do on the beamline. So you've got high UV transmission, could why that's useful in a minute. And we've got low X-ray scatter as well. So this film's not kind of starting to add background to the experiment. But the the oxygen impermeability and the ability to maintain an anaerobic environment, that's kind of the key driving factor. And that's kind of shown in these structures from that Patrick obtained some time ago with not with exactly this setup, but this is now much simpler than it was. But using quite a similar setup, you can see you get anaerobic and oxygen exposed structures using the fixed target setup, and that's something that's now relatively straightforward. Okay, so moving on to substrate driven reactions, we've got an acoustic drop ejection device, and that allows rapid substrate mixing. So you can see here in the video is in this case, this is just for illustrative purpose, we're firing water into an empty chip and recorded the video. It's significantly slowed down, but this is really quite a lot of work from really kind of driven by Pierre Aller, where he's put a huge amount of work into making the firing of the droplet really incredibly reliable and incredibly accurate. And then what that means is that we can fire a droplet containing the substrate into each individual aperture on the chip in time, as we raster through the chip. And something that we'll hopefully see the light of day very, very soon. And that's kind of together with Pierre, University of Bristol, and PAL is the firing of this avibactam onto this beta lactamase. You can see the avibactam binding in the active site on the crystals. Okay, so just moving on to light-driven reactions. So we're quite lucky on I-24 in that we have access to a high power pulsed laser system. So that's kind of a portable laser system that's kind of shared between 4 or 5 beamlines at Diamond. So every other run, something like that, we'll have the Porto for a week or two and be able to collect different and be able to use it for different laser experiments. And that laser light can be coupled right through to the sample, to the sample position. And then again, this is something that kind of can be modified, is a flexible approach. So this is something that was kind of really kind of pushed by Jasper and others. Imperial College was combining different forms of light excitation. So in this case here, what we had is we had two different, instead of just having a single pulse of laser light, we've got one pulse, which is kind of quite large and defocused, followed by a second pulse. And the reason that's useful is that for his particular protein, as it exists in kind of a mixed state, and with the large defocused light, what we could do is we could push it all into one state and then use the second pulse to drive to the second, and then start to look at this transition. But one of the limitations of laser light is only quite a small fraction of proteins naturally photoactivatable. And what we've been looking at a lot recently is how can we expand the reach of this? And photo cages are really kind of an attractive way of doing this, because what they allow is they allow you to make a non-light activated process light activatable. So we can use light to release the active molecule from some sort of from some sort of cage. And our current interest is in gas releasing photo cages. So we've got the NO cage and also oxy cage. I'll just talk about the NO cage today. Again, so this is using the setup exactly as I showed kind of a slide ago, with the Porto laser coupled through to the sample position and focused into a single aperture on the fixed target. So we did some initial work on the NO cage with kind of really with Pete Smith doing been kind of the driving force behind this, where we're kind of using this NO cage, which when we flash with UV light, which again highlights the importance of the UV transmission of the eval film that I mentioned earlier on. So we flash this with light, we can release the NO and then see, and then that then becomes accessible to the enzyme. So for the case study that I'm describing here, we're going to look at MCCP, and that binds NO at this heme site. Okay, so what do we see? So we see in the resting state, what we see is just a completely empty site here above the heme. And that's quite nice because it kind of gives us a potential on-off state. So it's kind of a little bit more of an obvious change. If we soak in NO, you can see the difference map here. And then you see the difference map here, you get a clear appearance of a nitrate oxide. And that's complemented by a spectroscopic change as well as spectroscopic change as well. So if you compare with what happens with the cage, again with the cage, you see the spectroscopic change exactly as we saw when we soaked in NO. So look, after a few typo there, but after a 9.5 microjoule laser flash, you can see the NO appears. And then if you look at the difference maps, then what's the take home here is that even when we go to very, very low laser powers, then we can see efficient release of the cage. So even when we've got low laser powers, we can see that NO gets released within the crystals, and then this is nice because it starts to make fast time points accessible when for substrate driven reactions, so you start to not be limited by the rate of diffusion in the crystals. Okay, so then just for the last slide, I kind of mentioned the Jungfrau at the start, so I won't say a huge amount about this at all. So this is a recent arrival at the beamline. So this was made possible last year through a BBSRC grant written by Mike, myself, Graham, who some of you will know, and Alan. And so the award of this grant meant that we could get this detector at Diamond. So why the Jungfrau? Why are we interested in Jungfrau? The key thing here is the readout. So this is probably something that you're familiar with as you kind of have ever increasing flux. Is the challenge with the Pilatus and the Eiger is as the flux starts to increase is the count rate. So when a photon arrives and it's above some threshold, then the counter increases by 1. But if the photons arrive too close in time, then they will just be counted as 1. And as the beam intensity increases and these peaks get more and more compressed, then that becomes a bigger and a bigger problem. With the Jungfrau and an integrating detector, we don't have that problem. So it doesn't matter how quickly the photons arrive in time, we'll get this increase in charge, and the readout value of the pixel should always reflect how many photons were incident on that pixel within the exposure time. There's some challenges associated with the Jungfrau that I kind of won't go into. There's a lot of experimental challenges where we need to cool the detector down to minimize the background and so on, but that's kind of work that we all have in hand. What I'll just highlight is that some of the data we've collected, the detector's working on the beamline. The data that we're collecting is really very good quality. So you can see that CC and our mesh is exactly as you would hope. And the background is actually very low. So this is actually a stack of 10 images, just so you can actually see something on the slide. But if you look at a single image, the background is kind of 0, 1, 2, 3, 1, 2, 3 counts. So the initial signs are the data look really spectacularly good. So this is something that we're looking forward to using over the next years. So yeah, just to kind of summarize and kind of bring things to a close. I kind of won't go through these I won't go through these kind of point by point, but kind of yeah, I kind of hopefully kind of showing that high energies can kind of help with standard crystallography and serial crystallography and fixed targets. I, I think we feel like they're an efficient way of realizing kind of serial crystallography at the synchrotron and at the FEL. And yeah, I guess as the final conclusion, the future, at least I-24, will be integrating. And then yeah, just to finish, this sort of thing is kind of these sort of slides are kind of the culmination of due to the contribution of a huge amount of work from a large amount of people. So there's the I-24 team and a lot of others at Diamond on helping with the laser, helping with the data analysis, data processing. Mike's done a huge amount of work. Key collaborations as well. Jonathan and Evo, Phil and Catherine, and then also the facility scientists, other sources as well. Okay, and so with that, I'll kind of stop. And if anyone wants to ask any questions, I'll be happy to try and answer.